Well, now we're on section 3.8 and we're doing question 45, and we have to use logarithmic differentiation to find the derivative of y with respect to, in this case, with respect to theta. So we're going to find dy d theta. But anyhow, let's, using logarithmic differentiation, we'll take the log of both sides. And so we get ln of the square root of theta plus 3 sine theta. And now, so ln of y equals, and by the law of logs, that's going to equal the ln of the square root of theta plus 3 plus ln of sine theta. Now let's take the derivative of the left, and so that's going to be 1 over y, and then by the chain rule, and then dy d theta equals. And by the way, now we're going to get 1 over, taking the square root of this term, the square root of theta plus 3, and now we'll go inside and we'll take the derivative of, by the chain rule, the square root of theta plus 3, and that's going to be 2 root theta plus 3. And then we'll take the square root of theta plus 3, and the d theta is 1, and square root, or the derivative of a constant 3 is 0. Now let's plus, and the derivative of ln sine theta, we put sine theta downstairs and take the derivative of sine theta, and we get cosine of theta. So now dy d theta, multiplying both sides by y, we get y times, and 1 times 1 is 1. In the denominator we have a 2, and root of theta plus 3 times root of theta plus 3 is theta plus 3. Plus, and it turns out this is the definition of cotangent. So that's cotangent of theta. And finally, y equals root of theta plus 3 sine of theta. So we're substituting this for y here, times 1 over 2 times theta plus 3 plus cotan of theta. And hey, we're done. Okay, now we're doing question 89, and we've got to find dy dx, and we need to employ some means of getting that exponent down in coefficient position. Well, the way we can do that is using the law of logs. I'll use the natural log, and so we have ln of x plus 1 is all to the x, or x plus 1, that quantity to the x power, and now by the law of logs we can pull that x down into coefficient position, and x plus 1. And by the way, the domain of this x has to be greater than or equal to negative 1, or not greater than or equal to, it has to be greater than negative 1, because you can't take the log of 0, nor can you take the log of a negative number. So this quantity in here will always be greater than 0, so we don't need absolute values here. Now, let's take derivatives, and on the left we're going to have 1 over y dy dx by the chain rule equals, holding x constant, taking the derivative of ln of the quantity x plus 1, we wind up with x plus 1 in the denominator, Then by the chain rule, we take the derivative of x plus 1, which is 1, and 1 times that is itself, plus. Now we'll hold ln of x plus the quantity x plus 1 constant, take the derivative of x, which is just 1, so we get 1 times ln of x plus 1. Now we'll multiply both sides by y so we can isolate dy dx. And that's going to be y times x over x plus 1 plus ln of the quantity x plus 1. And now replacing y with its identity, which is the quantity x plus 1 raised to the x power, and what do we have in the second set of parentheses? X over x plus 1 plus ln of x plus 1, that quantity, and we are done.